In this video, we're just going to take a quick look at whether there is linear correlation or not. We'll do a hypothesis test about this. The null hypothesis is always that rho is equal to 0, which means there is no linear correlation. The alternative is always going to be that rho is not equal to 0, indicating that there is linear correlation. R is our test statistic. There is also a t-test statistic that you could use. We're just going to be using our calculators and the p-value in order to do this, or you can use a table as well. Using the p-value, if the p-value is less than or equal to alpha, then we would reject the null hypothesis, and that would indicate that there is linear correlation. If the p-value is greater than alpha, then there is not linear correlation. If you want to use R, there is a table that I'll show you, and from the table, if the absolute value of the R that you calculate is greater than the value in the table, then that would make the conclusion that there is linear correlation. If the absolute value of the R that you calculate is less than or equal to the value in the table, then there is not linear correlation. In this example, we're going to take a look at example 1, where we did a hand calculation to find the correlation coefficient, and we found that R was 0.591. If we use a significance level of 0.05, is there sufficient evidence to support the claim that there is linear correlation between shoe print lengths and height of people? So the null hypothesis is always that rho is equal to 0. This indicates no linear correlation. The alternative is always going to be that rho is not equal to 0, and this indicates that there is linear correlation. So for our test, we have alpha is equal to 0.05. The value of n is equal to 5. There were 5 pairs of data in that sample. Our R value, the linear correlation coefficient, is 0.591. And now we want to find the value in the table that corresponds to this test. So in your formula packet that you got with your book, it's also posted in D2L under Content and in Course Documents. This is the table that we would use to do a hypothesis test about R. It gives you the values for n along the left-hand side, and you would just choose the n value that's closest to the one that you can find in the table. So once you get up to the larger numbers, then we see that not all of the values for n are in here, so it skips from 35 to 40. The value of n for us is 5. We're using a significance level of 0.05. We would be using this value 0.878. And we can see that the R that we have, the absolute value of that, is 0.591, and that's less than the value from the table, our critical value. Since our R is less than the value that we got from our table, then we're going to fail to reject. So we're failing to reject the null hypothesis. If we're not rejecting the null, it means we are rejecting the alternative. And failing to rejecting basically is accepting, right? And so that means that there is no linear correlation. We will be taking a look at doing this hypothesis test every time we do linear regression, and so in the next section of material we'll be testing for this a lot, and so we'll be doing several examples of whether there is linear correlation or not between two variables. In this next example we're going to look at how do we interpret R, and this is the explained variation. The value of R squared is the proportion of the variation in Y that is explained by the linear relationship between X and Y. So in this example, we're going to talk about the example 1 again, where we did the hand calculation for R. That was about the length of someone's shoe print and their height, and is there a linear correlation amongst those two variables. So we did this for 5 men. The data was taken from a larger data set that had 40 paired data values. The correlation coefficient for the entire data set is R equals 0.813. What proportion of the variation in height can be explained by the variation in the length of shoe print? This proportion is R squared. So we want to take 0.813 and square it. That gives us 0.660969, not rounding it at all. If I want to round that to 3 decimal places, that would be 0.661, and converting that to a percent, it would be 66.1%. So this 66.1% means that 66.1% of the variation in height can be explained by the variation in the length of shoe print. So lastly, just some common errors involving correlation. A common error is to assume that correlation implies causality. So a classic example involves paired data consisting of the stork population in Copenhagen and the number of human births. For several years, the data suggested a linear correlation. And so a big shocker here, storks do not actually cause births, and births do not cause storks. Both variables were affected by some other variable lurking in the background, called lurking variables, is one of the effects, the variables being studied but not included in the study. So a lurking variable is something outside of the study that is impacting both of the things that, or all of the things that you're looking at. Another error arises with data based on averages. Averages suppress individual variation and may inflate the correlation coefficient. One study produced a 0.4 linear correlation coefficient for paired data relating income and education among individuals, but the linear correlation coefficient became 0.7 when regional averages were used. So that's a pretty huge difference in the correlation coefficients, this one using individuals and this one looking at averages. A third error involves property of linearity. If there is no linear correlation, there might be some other correlation that is not linear. So just because something doesn't have linear correlation doesn't mean that there's no correlation between the two variables. So it could be exponential correlation, or it could be quadratic correlation, or some other kind of correlation that's going on between the two variables. Coming up, we'll take a look at linear regression, and so how do we find the equation of the line that best fits our data, and we'll also just make sure that there really is linear correlation and that we can use the regression line that we come up with. So that's the next topic that we'll be talking about. I hope that you're having a great day.